All right. Hello, everyone in the future on YouTube. Today, we are going to learn some data types in Lean, and I'm going to use this chance to do some comparisons with algebraic data types in Rock/Coq as well, because turns out that was the content of my master thesis at Purdue, which it's gonna be a 1 year that I just completed my master's. Jesus, time flies. Then I went to Europe and then that's when I started producing content for you guys. And here we are, trying to make a living out of this. So yeah, I'll take this opportunity to humbly request your support if you're able to. We just opened a marketplace last week, so if you guys could go check out the TTForall marketplace, is ttforall.myshopify, and have some pretty dope shirts and hat and mugs and all the cool stuff we ship internationally. That would be awesome. We're trying to raise some money to go to Zurich, the biggest Haskell event in the world. So I would really appreciate your guys' help. But let's go ahead and start talking today. Today I'm gonna start with Rock, actually. Start with Coq to show you a little bit of my expectations. As always, I don't know any Lean. I don't know what to expect out of data types in Lean. So I'm gonna show you a little bit of how algebraic data, what I think about when we talk about algebraic data types, and then we're gonna go and step into Lean. Feel free to ask any questions. I will be asking a ton of questions because I have no idea what is going on in the Lean side. But to be entirely honest, I do not expect to be too different from Rock, from what I know, from what I expect in Rock/Coq. So, and the reason for that is because algebraic data types is very difficult to get right. Okay. So this is a Boolean with two constructors. I suppose you guys should be kind of familiar with this. If you have some functional programming background, I have no idea what is the background of the people watching. I think I'll assume some functional programming background. Let me know if you don't know Haskell or OCaml or maybe a little bit of Rust. You can do this kind of stuff. So, algebraic data types constitutes of a new type. You're like building a new family, let's put it that way. And the constructors are exactly the only way possible to build those types. And this is how you construct a data type. And then once you have a data type, you can build functions around them. So for example, you can have NB, which takes B1, B2 of type Boolean and can return another Boolean. And this is the coolest part of algebraic data types, is that you can destruct them, right? So if B1 is true, well, if B1 is false, then the whole end is false. But if it's true, then we match B2. Well, we return B2. We can return B2 directly. So it's going to be exactly what B2 does. And then you can use that to do some computations and say, okay, and B, true, true. This will be true. We can see here in the bottom. And B, true, false should be false. False, false should be false, which is correct. And finally, false, true should also be false. Okay. Yeah. Yep. This is the simplest algebraic data type you can have. And then you start having some notion of recursion with say lists, right? Induction or inductive, where it's kind of a type of type, and then you can build a single constructor there. And you can have cons that can take an A of type A, well, A to list of A to list of A. Yeah. And finally, the coolest thing about theorem provers is that we have the notion of independent types, inductive vector, for example, where it's also parameterized by something. Well, the thing now is that it's not only parameterized by something, but also trying to remember if we, okay, yeah, this is still a parameter, doesn't need to be an index. So this thing on the left hand side of the column in Rock, these are the parameters. It cannot change. So every time that you're building something, it must return the list A. But when you have something as an index, then this can change, and I'll show you how that will come at play now. Because, for example, list for a vector, for example, it's going to be a vector A 0. The nil is saying that it has 0 of length, right? And vcons is going to be a Forall and of type net. I have can have something of type A, and if my tail now is of size n, now the final type of the vcons is going to be s of n. And now things start getting kind of interesting, because let's see if I can do the append for vectors. That shouldn't, it's not gonna be too bad. Arguments vector. Okay, arguments. So the reason why I'm doing these arguments now is to say that this A is going to be implicit, because I don't want to be writing that all the time. Okay. Vcons. Okay. And that. Okay, yeah. I think now it's what I would expect. So now v append, it takes v1, v2 of type vector, and they can have different types, I think. Can have n1 and 2 of type net, and then vector a and 1. Well, v1 has type vector a and 1. v2 has type vector a and 2. Okay, I think this one shouldn't be, because otherwise I want to write vector a and 2, and all this should return vector a and 1 plus and 2. Okay. Okay, so now how we do this, that match v1 with vanil, return v2, and match vcons a1 a and xs with should be now, I put a here on top and returns vcons, well, and returns v append, and okay, now vcons xs has size n2, things start getting pretty complicated for doing the append now, because we have to carry around and change the types of the subterms. And I forgot for a second that we're not dealing with lists anymore. So the append of, I think N1 and N2 should also be, yeah, they can also be implicit here. And now the append will take XS V2, I think. But this will fail because, okay. Vicons, yeah, Vicons have, so N in Vicons should also be implicit. And boom, okay, the append works. So if I do example exercise 1, if I do the append of vinyl, let's just compute right away. The append of vinyl should be, okay, good. But I don't know what the type is because I never said. Okay, now it's of type net. And curious if I could do this instead. Net. Yeah. Okay, same thing. Okay, and now I can do a Vicons, yeah, vinyl with Vicons 3 vinyl, right? And what if I do a Vicons for vinyl? Now it will be, yeah. Okay, should be working. And notice that it doesn't really compute the 1 plus 1, it just keeps tracking them. I could also Vicons 3. 1, 2, 3. Yeah, nice. Okay. So this is more or less what I expect from the Coq side. And the reason why I just went ahead and printed the definition of the append is to show you guys that under the hood, this is the definition that Coq is learning, is storing in the back. And I keep saying Coq because I've been saying this for like 10 years, but it's now called Rock, and I'm still having trouble to remember the name changes and all of that. And what I wanted to show you guys is that the pattern matching here is quite more complicated than what I actually wrote. And the reason for that is because when you're talking about dependent, like things with indices, I think index is such a weird word in English because singular is index, plural is indices. So like it really changes the how you speak things. Index, indexes. I would expect indexes. It's indices. Anyways, this is an index because it can change, as I said, right? So for one constructor is one thing, 0 in this case. For the other constructor is successor, so like something else. So since things can change, the type of things can change around as you pattern match, then you need to tell the pattern match how's that change happening, how's that change, like what is going on under the hood. So I'm not gonna spend too much time telling you what each one of these things are gonna do. I'll leave that for the cock rock series that we're doing. Um, but the main idea I wanted to show is that things get complicated. This is a dependent pattern matching. This is, I want to say, it's pretty complicated. It's one of the most complicated things in type theory. I'm thinking if I can actually say that, because like it's very easy for me, who spent a whole master thesis thinking really hard about these ideas, to say, oh, this is like the most hard problem that we can have. But but it's hard. It's non-trivial. Anyways, this is a brief introduction of algebraic data types and algebraic. So simple algebraic data types, simple parametric types, and then indexed types. Another example that we do very often is a little compiler, like a little interpreter for a simple language that would show the power of why, like, then the dependent pattern matching would start showing up. But since this is not a rock thing, and I've spent too much time already talking about rock, I'm not gonna go there. But I definitely want to see, like, the thing that I'm the most curious today is to see how Lean deals with dependent pattern matching, if this chapter talks about it at all. I wouldn't be surprised if it doesn't, because this is the functional programming part of the book, and you don't need things to be too fancy to do functional programming, right? Um, Let me see what is the next part of this chapter. So yeah, it starts talking about polymorphism, and then later starts talking about, well, okay, this is what I'm looking at now. I was showing you guys this the lean part here, and there are some type classes. Oh, nice. They're gonna show some monad stuff. That's nice. Oh wow, it goes all the way to monad transformers. That's fun. Okay, here's what I would like to see. I might be curious enough to go ahead and jump straight to this chapter later, at the end of our session here. So I really want to see how it does things in this case. But I might not have enough background to understand what is going on. So anyways, let's go ahead and learn data types. And for this, we are going to use our Lean. Let's create a new file, datatypes.lean. Datatypes.lean. Oh, I close data types. There we are. Eval 3, I guess. What happened to the how do I open? Oh no, I have no idea how to reopen the Lean output thing. New project, server restart file. Show output. No. Build documentation, Unicode abbreviation, restart server, maybe. Project folder. Oh, I think it's this. Wait. Yeah, nice. Okay, we did it. What is this? What is wrong with this? Why is this complaining? Okay. No. Okay. Can I have a thumbs up from someone to say that that you guys can see my screen, that you guys can read things? Don't be shy. I think I will go ahead and assume that everything is fine. Feel free to chime in then at any point. Okay, so let's go ahead and start seeing what is this book about. Structures enables multiple independent pieces of data to be complained, blah, blah, blah. Types such as a structure that group together a collection of values are called product types. Can be as structures. Application might need track users' permission, where it's number of binary operations. Structures do not provide an easy way to encode multiple choices. I see. So this is giving an interesting background on how things need multiple choices. Excellent way to keep track of fixed set of fields. For a number of elements, classic data structures as string lists have recursive structure. Talk how these data types are going to be recursive. Expressions being also recursive. Some types. This are called recursive data types. Recursive sum types are called inductive data types. Induction may be used to prove statements about them. Because mathematical induction may be used to prove statements about them. Okay. I'm thinking about this statement. The reason why it's called inductive here being mathematical induction. I'll take it. In programming, inductive data types are consumed through pattern matching and recursive functions. Consumed through, yeah, I keep doing this little, like, thinking about how things are written, because I really appreciate how David is a good writer. And in this case, I would be trying to relay the idea that inductive data types are, like, they're made of these constructors, and then when you're using them, then you have their kind of like the destructor counterpart, which is the pattern matching, right? Okay, so we have built-in data types, for instance, boost and inductive data type, like this. Can I have check bool? Yep, it's already defined. Can I print bool? Bool constructors false and true. So the first line is saying that the name, the new type is a bool, and the rest are the constructors. Constructors has the structures. Constructors inductive data types are just receivers. Unlike structures, inductive data types may have multiple constructors. Here, there are two constructors, true and false, and neither takes any arguments. Structure declaration places its name in namespaces named after the declared type, and inductive data type places the name of the constructors in a namespace. So true and false are re-exported from namespaces so that it can be written alone. But in general, it would be bool.true and bool.false. Gotcha. Okay. Data modeling perspective, inductive data types are used in many of the same contexts, where a sealed abstract class might be used in other languages. Languages like C# or Java might write a similar definition of bool. Specifics are fairly different. In particular, allocated data, so true and false are both types, more specific type. While Lean definition introduce only the new type bool. Well, the other thing that it failed to address, well, that it didn't say, but it's in the back of my mind, is that the main difference here from C# and Java, the reason why we did not call this an algebraic data type is because in this case, true and bool is not closed under true and false. Okay. In this case, the only ways for you to come up with a bool, something of type bool, is either with a false or a true. And in this case, you can come up with a bool as with a true, and you can come up with a bool as a false, but there is no assumption that these are the only ways. And in fact, I don't know much of C#, but I know for a fact that Java, you can extend things as you go. So you could add other constructors later. And this breaks pattern matching. So the main difference between, things like this in OO and what we're usually going to call functional programming language that you're going to have in an algebraic data type like this is exactly your capability of performing pattern matching. And in order for you to do proper pattern matching, like type safe pattern matching, you need your data type to be closed under the constructors. You need to know that these are the only ways to build these constructors. That's very important. And if you don't have that, then that's not great. I forgot to turn on my light so that I could look a little bit better, but okay, I addressed that now. And this is one thing that I get a little frustrated that I criticize in Haskell a little bit is I don't know how things are in Haskell these days. I think last time I programmed in Haskell were maybe 4 years ago, so I don't know how things are these days. But when I used to program in Haskell, by default, there's a flag that you can have non-exhaustive pattern matching, and that would be very, very nice thing to do due to laziness, because then you didn't need to write down all the cases, and your function would still run and then maybe get stuck or maybe break if you didn't have all the cases of the pattern matching. But that makes your language really unsafe. So I don't love that about Haskell. I don't know if that's still a thing. I know that there is definitely a flag that you can turn it on and off. Hola Pedro, soy nuevo, no entiendo el idioma, pero aprendo observando. Saludos, salud. ¿Qué tal? Mi español está muy, muy malo. Hablo muy poquito de español. Soy brasileño, pero hablo gringo. Sorry. we call Spanish speakers in Brazil gringo. It's not a bad thing. It's just how we call anyone from any other country. But I know that maybe in Spanish it's a little bad to say gringo, but in Portuguese it's very 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 normal. It's not a bad thing at all. So welcome to the chat, Anderson. Bienvenido. Okay, So now it talks a little bit about net. I think I'm gonna write these things as in let me see if I can try to talk little español, un poquito español. Aprendemos hoy estamos aprendiendo poquito de Lean. Lean estas provador de teoremas iterativos e podemos fazer coisas muito legais. Sorry, meu espanhol é muito malo. Posso falar em português, se vocês quiserem. Você consegue entender alguma coisa de português? Português também, ó, top, top, top. One thing that I...
Nacho232425 just followed.
Thank you for the follow, Nacho. One thing that I find very, very funny, una cosa que pienso ser muy, muy engraçada, estas que falantes de português podemos entender el español, pero a falantes de español no entienden mucho de portugués, que es... I think it's funny. So yeah, Portuguese speakers, we can understand Spanish kind of, but Spanish speakers cannot understand Portuguese, which I find very, very amusing. But pero no puedo hablar español mucho hoy porque estamos indo al YouTube. So let's just focus in English. So what I was gonna say is that I'm gonna do the bowl here and do a little false bowl and true. Pô, eu sou brasileiro, cara. Tá achando o quê? Tá me estranhando, meu irmão? Pô, mano. Pô, tô pagando de gringo aqui. Tá me estranhando? Sou goiano pé rachado, meu irmão. Oxi. Olha lá o cara, tirar onda. So, vem falar que sou gringo não, tá maluco? Oxi. Cara. So what happened here is that someone is asking if I have fluent Portuguese, and I fake get mad here. That come on, man, come on. Of course, I'm Brazilian. Of course, I have fluent. But wow, yeah, I'm quite flattered. Thank you. Like that means that my English must be good, reasonably good. But well, I lived in Australia for a year. I lived in the West for 6 years. So yeah, I'm kind of I feel comfortable speaking in English. I definitely do think I do have a little bit of an accent. Like English speakers will know that English is not English native speakers will know as a fact that English is not my mother tongue, that I'm not a native speaker. And that doesn't bother me at all, because you learn that your accent, like as long as people can understand you and you can understand people, your accent is your birthmark, is your watermark, is what distinguishes us. I don't wanna people to think that I'm American or European anyhow, because I am American, and I'm not American. I am Brazilian, and I am very, very proud of being Brazilian, and and I carry that everywhere where I go. So I don't want to lose the little bit of the entirety of my accent. Anyways, I don't care about that. Oh, cool. So Nacho is saying that he's from Uruguay and he lived in Brazil for 6 years. Yeah, man, I love some. The time that I was in the West, I've made a lot of Latino friends, and I learned how to dance salsa and bachata. You know that we don't really dance those here in Brazil. We dance forró. So it was fun to learn salsa and bachata. I think I learned like a year of lessons. I had a lot of, especially Colombian friends. I have some friends. I have some there were some girls that I got pretty close to. I'm trying to yeah, okay. So one of them was from Paraguay and the other one from Uruguay. I'm very upset that I didn't like I traveled a lot in the US. Been doing trips in Europe, but I never did trips in Latin America. And I'm ashamed of that. I'm ashamed of that because we have free passport to all of Latin American. So I should be enjoying better. We have a lot of really nice, cool things to see in Latin America. So um, the bad thing about like for Brazilians is that we don't really speak Spanish, so that makes things a little harder for us to travel around. But we can get around. We can do some portunhol. So ¿qué lenguaje de programación recomienda que están en el auge de trabajo hoy en día? So Anderson is asking what are the programming languages that is peaking these days. I don't know, like TypeScript, Next, Vue, Python, Java. Java had its days. I don't know. I'm not the best person to answer that question. Um, if you guys can translate to Anderson what I'm saying, I'm not gonna be trying to speak Spanish anymore. That was enough. But because otherwise can get a little boring for the English speakers as well. But what I was gonna say is that I'm not really the best person to answer what are the good programming languages for the work, like the market, like for the industry, because what we do here is programming languages research, and for us, to be entirely honest, in the end of the day, all languages are kind of the same. They have a little bit of different philosophies here and there, and they prioritize different things, and they try to solve different kinds of problems. But at the end of the day, if you squeeze your eyes enough, it's all the lambda calculus. All the way down, you find lambda calculus over there. Very hidden little beautiful pearl in there. But the lambda calculus with inductive types. Inductive types is hard to have well done in other languages. And this reminds me one thing that was very important for me to say about Rock that I didn't, and I'm gonna show you now, is that once you define a data type like this, it also comes for free for you something called, let me show you. So if I run this line here, we're gonna see here that it has defined a bunch, define the type of list, but define a bunch of other definitions. And this is the coolest part. If you come here and you print these definitions, we're gonna see that it also generated, well, not print, let's check. It also generated the induction schemes. So when you're doing a proof by induction, you're actually simply applying this theorem that was generated under the hood. So this is the power of the calculus of inductive constructors, because what it means is that it adds not only dependent types to your language, but also inductive data types. And this is the real power of what Coq and Lean are doing, is because you're dealing with very fancy types in your lambda calculus, which is called the calculus of constructors, plus algebraic data types done right. And in order to do algebraic data types right, you need an algorithm to safely produce the induction schemes, because these are the things that are going to be used to prove the proofs by induction. Okay, it's this. Oh, I just noticed that part of my face is in front of this here, but I can take it here. This is the full definition that is showing over there. So after PL, there is also the pcons here. You don't need to understand what is going on here, but this is saying that in order to prove a property over a list, you have to first prove that property on one constructor and then prove that property on the other constructors. And the constructors that has a recursive call, then you have that recursive call as a hypothesis to build what? Your induction hypothesis. Yeah, you have it as a hypothesis. The same property, but for the smaller element, the recursive call, you can assume that as a hypothesis. That's induction for you. And it's beautiful. It's gorgeous. It's very nice, very nice. And I am curious if that's exactly the same for bool. And when I printed bool here, I'd maybe expect to see that somehow. But anyways, let's keep going. Let's keep going. Maybe I will be able to print the recursive schemes for this in Lean at some point. Remind me to come back at that and try to print the induction schemes, because I wanna take a look at them. I wanna compare with Rock, and I would expect there to be kind of the same. Anyways, let's move on. Let's move on. It's been we're making progress very, very slowly today, which is good. We're having a good time. We're chatting here. Feel free to chime in and chat and ask questions and tell me if there are any interesting things that you know or you want to know that I might know, and we can talk about it. Okay, so now he comes here. Okay, and have different representations. Okay, and now it's talking about Peano natural numbers. Raise the hand if you guys don't know Peano with natural numbers, and I'll take more time to explain it. But I'm assuming a little bit that you guys know. But if you don't, let me know, and I'll go slower here. Okay. 0 represents 0. Suck represents +1. Net, the recursive type. Successor means 1 greater than. So successor of 5 is 6. Successor of 32. This is an interesting number. Why did David pick this number? Why did you pick this number, David? There must be a reason. So the definition of 4 is suck, 0. Definition sounds like the definition of both, slightly different names. Only difference that suck also carries some information and true does not. Name 0 and suck are spaced, and that blah blah blah, same thing. Argument names such as n may occur in Lean's error message and feedback provided by writing mathematical proof. Lean also has optimal syntax by name. Generally, however, the choice of argument name is less important than the choice of a structure field, as it does not form as large a part of the API. In C# or Java, not can be defined as follow. There's a type here. Recursive. Interesting. It's interesting for me how he's explaining data types in terms of OO. Like he's comparing data types with OO. I'm very curious what he's going to say when pattern matching comes. This is the bool example above. This defines more types than the Lean equivalent. Additionally, this example highlights how Lean data types like subclasses of an abstract class and their structures in C# or Java. Organization code to be executed. Some types are also similar to using a string tag to encode discriminated units. TypeScript. Script net could be defined as follow. Wait. Lean data types are much more like subclasses of an than their constructors. Structure shown here, instantiation code to be executed. Some types are also similar to using a string tag to encode discriminated union in TypeScript. Interface 0, interface suck. I think this encode ends up with more types than in Lean because zero and suck are each their own. To illustrate that Lean's constructor responds to object TypeScript that include a tag that identifies its content. I don't know any TypeScript. I don't wanna know much TypeScript type system of why this tag is necessary. But I would assume that this is an equality thing to discriminate between the interfaces. And I'm a little bit disgusted right now. I'm gonna be completely honest with you guys. JavaScript kind of disgusts me a little bit. So let's ignore that. Okay, pattern matching. Pattern matching, which for me is one of the most beautiful things in programming languages, design, and this is the heart of what we call functional programming languages. Yeah. What's his name? I interviewed a guy. So TTForall, we're a podcast, and we have more than 80 hours of content in type theory and programming languages. If you guys are unaware, go check it out. Also check the marketplace, buy stuff, keep us running. But what I was gonna say is that Bell Labs, well, not Bell Labs, David McQueen is the guy who basically invented algebraic data types. And I got this beautiful opportunity to have a very long conversation with him. So the first day was a 2-hour conversation. The second day was a 2-hour, 10-minute conversation. And I got the chance to ask him, like the story behind what he was thinking about algebraic data types, how they came up with this. They were playing around with this programming language called Hope. And they invented algebraic data types, which is very cool. So then like he went and started working at Bell Labs at its prime. And for those who doesn't know, Bell Labs have like 10 Nobel Prizes and like 5 Turing Awards. And has been running for almost 90 years. It's a huge research institution. So I was very curious to ask him a lot of questions about how Bell Labs work and how things like why is it so cool over there. Anyways, all of that to say that this is pretty much the inventor of algebraic data types and pattern matching, for all that matters. And in the paper where he introduces Hope, I forgot the name of the paper. Hope. Let me see here. Maybe I got the link to the paper. Yeah, here. An experimental applicative language. In this paper, they talk. The reason why they call it algebraic, like that paper, they make it clear that when you define your data type like this, then you also define a couple of equalities to make sure that things behave nicely and as you would like them to behave in order to make pattern matching. And pattern matching is like that the idea of the paper is that you could program by kind of like defining equalities by saying like, okay, is 0 when n is equal to 0 or when n is equal to suck will behave like this or like that. That is like how the name algebraic came in, like this notion that algebra is dealing with hanging around with equalities and defining structure over your stuff. So that's a nice little piece of trivia for you guys. Okay, let's see what we've got for pair matching. Data are consumed by first using first test operator, check which subclass is saved, and then when the values of the fields are fitted to the given subclass. This is so interesting because, yeah. So David is clearly thinking, like reasoning, teaching for the regular day programmer that not necessarily is a functional programmer. I think that's why he's comparing with these other languages. So that's why he's talking here about instance of and subclassing. Check which codes to run, ensuring all of the data is available, while fields themselves provides the data. Both processes simultaneously served by pattern matching. Yeah, that's the thing because, okay, so the first one is that should determine which code to run, and then the field provide the data. Okay. But I think, thinking here of differences, I don't have much familiarity of how instance of works in Java, but I'm pretty confident it should be dynamically, like it's kind of like a dynamic dispatch kind of thing, because like it will go into the memory and check what is the type of the data in that piece of memory. And pattern matching is entirely static. It doesn't go, like, everything is done in compilation time during type checking. So it's more powerful in that sense. It's giving you more guarantees. That's why pattern matching is so beautiful, I want to say, because you're really talking about the type system here. This is the kind of beautiful thing we do in programming languages research. Okay, so is 0, def is 0, and of type net and bool, match, and with net.0 turns as the true, net.k returns false. They're complaining. Express provide the function arguments, and for destructing, fan was constructed by netsuck. Then the second branch is taken. The result is false. The step evaluation is 0. Net 0 proceeds as follows. 0 net 0. Let's see. Eval is 0 net 0. True is 0 net suck net 0. False. True, false. Can I just say 0 and print net 0 net suck? But I can say true. I can say false, but I cannot say 0. Well, of course, it's going to be like 0, right? So nobody cares about the actual name of the constructor that has been built under the hood. Interesting. Okay, I'll take it. It shows 0% similarly. The k second branch pattern in 0 is not declarative. Makes an add take the argument suck visible. the name, the similar number, the smaller number can be used to compute the final result, but it doesn't use in this case. So it also gives us a warning. Maybe when the book was written, it didn't give warnings back then, but we don't like warnings. How do I turn off linter stuff? Set. I don't know. Does underscore work in the pattern matching like other functional languages? Well, what I expect that the underscore here is doing is to not name the variable. Just saying that there is a variable here that I'm not using the name. I'm not gonna use it anywhere. So that's what the underscore is doing here. I don't know if that's what you're asking, Connors. But yeah, it's just kind of like throwing away the name in this case. Successor of some number n is 1 greater than n, that is n plus 1. The predecessor of a number is 1 less than it. If pred is a function that finds predecessor of net, then it should be the case. Following. So pred is already defined? It's not. Wait. So wait. Oh, okay. Here's the definition. Def pred. Net returns a net, and then I pattern match n with net 0, net 0. That's okay. Oh, yeah, now I need the k. Because if I do not give it a name, then I don't know what k is here, and I cannot just leave it behind because that doesn't make sense. So yeah, that's how things are working. So now, yeah, eval 0, 0, 2. Yeah. What is a big number that I was curious why he picked it? It was 32,186. Right. 32,186. Oh, what? 8? What the? Just what did I do? Oh my god! I think I broke. Yeah. Oh no. So I ran a vim command and I made this humongous number here, and I think I crashed Lean under the hood to try to run this little beast of a number. It's like it's a humongous. Oh shoot! It's still generating numbers. I wanna throw. Oh god, what should I do now? Connors was whether Lean treated the underscore as part of the pattern match that they don't care about. As a yeah, I think so you agree that this is like that's what happened, right? I know. I think I know how I did it. Actually, it's like I pressed a big number, like 32,000, and then like I wasn't in insert mode, and when I got into insert 3, then it thought that it should insert this number or whatever a lot of times, something like that, like it was, I believe it was a repeat, like because I was not in insert mode when I thought I was in insert mode. Oh no. Oh no. Let's see what I can do about this. Oh god, here's what I'm gonna do. I'm gonna go under the hood here, and I'm gonna edit this file. Gonna add this file here. I am actually in the command line elsewhere that you're not seeing right now, but I'm gonna deal with this my way. Fam data types .lean. Oh boy. Ooh, it's getting worse. Oh god. Okay, this is what I'm gonna do. Okay, it's gonna turn. Oh god. Yeah, repeat, rewrite, flashback. Oh god, what have I done? My computer is starting to overheat a little bit because OBS is taking considerable amount of. Oh wow! Look at this. I think you guys cannot see what I'm seeing. Let's see if I can show you. Yeah, you cannot see it right now. Okay, look at this. Wait. Yeah, can you see here? 20, 30,000 lines and counting. Jesus. Oh, there you go. It keeps going. Oh man. Okay. Okay. That's fun is over. Fun is over. Let's actually fix it now. Okay, there we are. We're done. Bye. Bye. It was so funny. Okay. Nah, that's 0. 10 0. Okay. Okay, that's it. We're done. All I did was turn off the actually close VS Code so that it stops computing and then open it again. And we could fix things. So you're done. Okay, let's keep going. And net, the name used refer to net underneath. Okay. Find function to 5, gets 4. Yeah, whatever. Pattern matching can be used with structures as well with some types. For instance, a function that extracts the third dimension from a point 3D. Oh, do I have access to point 3D here on this file? Because it was defined on another file altogether. Point. Point. How do I import something in Lean? Import structures, maybe? It must be used at the beginning of a file. Unknown module prefix structure, so maybe lean.structures. Check file. Oh, lean does not exist. How do I import a lean file? How to import a lean file? Files. Page not found. Lean4. I want to import some mathlib. Wait. Terminal, go to the folder you want to create a project. Go inside my project. Importing files. If you want to use additional file, however, it needs to be imported manually via import statement at the beginning of file. Imports the file full. Okay. And imports are out of date and must rebuild. Use rebuild restart file. Okay. Failed. Okay, I think it's finding the right file now. Oh, but things are very broken. This file. So now, maybe if I restart the file, things are gonna work. Ooh, fancy. And if I do checkpoint, it works. Nice. I did it. I did it. Nice. So we also have 0.3D, right? Good. Good. So we can continue now. Okay. Def P 0.3D. So float. Match P width. Oh. H, Y is W, Z is T. And it's again, I think it's going to complain about unused variables. Oh, give it a name. Yep. Complaining that H is unused. Complaining that W is unused. Don't care about those. I wonder if I can do let. Yeah, if I can do like this. SP and D. No. No. Ah. Cool. Cool. There's a name for this kind of let. It's called singleton. Some kind of singleton something. Because there's only one way to match P here. Since 0.3D is an algebraic data type with exactly one constructor. Not eval. Print. But it knows under the hood that is a structure, so it prints as a structure. But as we saw in the last chapter, this is defined under the hood as one single algebraic data type. Like it's an algebraic data type with a single constructor. So I think the name of this is a singleton elimination, something like that, I guess. I don't know. I think. Okay. Just use Z accessor. But structure pattern are occasionally the simplest way to write a function. Yeah. So yeah, so this case would be p.z, right? Yeah. Okay. Okay. Then we have recursion. Definitions that refer to the name being defined are called recursive definitions. Inductive data types are allowed to be recursive. Indeed, NAT's an example of such a data type because suck demands another NAT. Recursive data types can represent arbitrarily large data limited only by technical factors like available memory. Just as it would be impossible to write down one constructor for each natural number in the data type definition, it is also impossible to write down a pattern match case for each possibility. I was joking. I was reading as kind of like a joke and I didn't understand much. So I have to kind of read again. So that was kind of like pretty dumb of me. Very nicely complemented by recursive functions. Simple recursive functions with nets. Checks whether its argument is even. Oh, I see. It's actually showing how recursion is useful, I think. I guess. Okay. Progressive portion is check even. Non-cursive branch of this code. Like this one are the base cases. Successor are odd numbers. Successor of even is odd. This means that a number built with suck is even if and only if its argument is not odd. Edge and width. That's 0. True. That's okay. Not even k. Not even k. This is not even k. That is funny. Spider-Man is thought is typical writing. Let's check it. Evolve even 3. Nice. 2. 1. 0. 32, 135, 3. Huh. Likely to a Stack Overflow. Oh, maybe that number is the number that overflows. 185. I have to restart the server. 32,100. 100. 8. 4. 5. Ha! I told you there was a reason. This is 32-bit divided by 2. Is this that number? It's I'm looking at my calculator now. You guys are not seeing, but let's see here. 2 to the power of 2 to the power of 32. No, this is much larger. Of course, this is true. Just much larger. Maybe 8-bit. No, of course not 8. 10. 2 to the power of 10. It's 1024. 2000 to the power of 16, maybe. Yeah, and then divided by 2. It's 32,768. So weird. It's not 16 bits. That would be 16 bits that would overflow this. Wonder why. It's like it's 16 bits minus 32,185 minus 1,000. 1,166. Such a random number. But yes, these numbers are the numbers that overflows. That for some reason overflows Lean. Maybe it's only for this function. I don't even know. So let's leave the 84 there. Wait. Oh, this also overflows. 7, 1, 0, 0, 1. Everything's overflowing now. Yeah, I think I have to restart things. Yeah. Oh, maybe I was looking in the wrong place. I was looking down here. Whatever. Let's just put, I don't know, like, okay, this, whatever. Fine. Just curious. Find predecessor of net. The first step, check constructor was created. Yeah, we did all of that. Okay, find the function 5. Okay. Depth. Wait. I did that already. Okay. Okay. First at 5, what you do is 0. Determine how to transform a result for an arbitrary net, result for its successor. Apply this transformation to the result of the recursive call. This parent's called structural recursion. It's important. It's important that I only have structural recursion over strictly positive constructors. Otherwise, you have non-termination, and non-termination leads to inconsistency in your logic. Programming languages usually do not care about consistency of your logic because you don't usually use programming languages to prove theorems about your programs. However, interactive theorem provers care a lot about consistency of your logic because that's what is going to guarantee the correctness of what you are doing. So you do not want to have a non-termination in your programming language, in your interactive theorem prover, because that would be inconsistent and you can prove literally anything, such as 1 equals 0, 0 equals 3, 3 equals 1000. So what good would that language be? So it'd be useless. Unlike many languages, Lean ensures by default that every recursive function will eventually reach a base case. From a programming perspective, this rules out accidental infinite loops, but this feature is especially important when proving theorems where infinite loops cause major difficulties, which I just talked about. A consequence of this is that Lean will not accept a version of even that attempts to invoke itself recursively on the original number. Fail to show termination for even with errors. Fail to infer structural recursion, not considering parameter of n of even. It is unchanged in the recursive calls. No parameter is suitable for structural recursion. Even though addition takes 2 arguments, only one of them needs to be inspected. I'm going to use M because I'm cooler than the book, and K. Who uses NK? I'm going to use M. With. Don't tell me what to do. So when the right-hand side is 0, left-hand side, if it's a suck. Why is it pattern matching on the right-hand side of the plus? So weird. So it's not the usual definition of plus. Add. Ah, look at that. Look at that. Look what just showed up. Dependent pattern matching. Exactly what I was looking for at some point. Cool. Cool. What is that below? Wait. Motive net, some sort. Net below and a universe U. Yeah, I'm pretty confident this is a universe because it's calling over a sort here. I'm not sure if I'm going to explain this to you guys at this point. So what this does is to take the number together with a motive into this universe U or 1, whatever is bigger. Either, why is that called below? Match motive. Take an net, take an X. Okay. Net below. With the motive being net. Tap extra net. Oh, X is applied to the motive or to net below. Thought it would be X arrow, but arrow binds less tightly. Anyways, let's stop here. I was just trying to understand a little bit of what the dependent pattern matching was doing, but that is pretty hairy. It's pretty hairy. I just got quite curious at this point, and I got a little carried away. But I'll come back to it eventually on a better, like actually reading some better documentation on how dependent pattern matching works, because I think that's very interesting. Okay. Definition of plus, the name K prime is chosen to indicate that it is connected to, but not identical with the argument K. For instance, walk through the relation of plus reach, use the following steps. Yeah, there's a pattern match, and then, yeah, it takes plus inside. Wait. Plus 3, suck. So I matched suck. And then it returns this one. Right. So yeah, and that's suck plus K prime, and K prime now it's gonna be suck 0. Same thing, and now it's gonna be net 0, and now it's gonna be 3. Suck 3. When we should think about addictions that apply suck K times to 1. Similarly, in multiplication, this K adds and subtracts its predecessor. Def times and net K net match K width net 0 net dot 0 net dot suck K prime and plus n times n K prime def minus and net K net match K width net dot 0 and net dot suck K prime pred minus n K prime. Okay. Not every function can be easily written using structural recursion. The understanding of addition is iterated net.suck. Multiplication as iterated addition and subtraction as iterated predecessor suggests an implementation of division as iterated subtraction. In this case, if the numerator is less than the divisor, the result is 0. Otherwise, the result is a successor of dividing the numerator minus the divisor by the divisor. I'll just believe it. This is called long division, right? This is long division. It is, right? Div and k net if n is smaller than k, then 0s. Yeah, this is gonna complain that it's not the structural recursive. Yes. Nice. Failed to infer structural recursion. Cannot use parameters n. Failed to eliminate recursive application of div n minus k. Cannot use parameter k. Failed to eliminate recursive application div n minus kk. 2 times. Cannot guess if n is what is getting small or k is what is getting small. Quite frankly, it's n, but you have to show that. As long as the second argument is not 0, this program terminates. It always makes progress towards the base case. However, it's not structurally recursive because it does not follow the pattern of finding a result for 0 and transform the result in the smaller net into a result of its successor. In particular, well, so how I would, in particular, the reciprocation of the function is applied to the result of another function call rather than input of constructor argument. Yeah, this is what I was gonna say. This is how I would explain it. It's saying that you're doing the recursive call on like something that was not a result of a pattern match. So this one, the decreasing argument is a direct result of a pattern match. This one, the recursive argument, is a direct result of a pattern match. This one, the same thing. So that's how it guesses the decreasing argument, because it's really syntactic. It's really straightforward. But in this case, it requires a little bit more of reasoning to show that this is actually decreasing. And this is a undecidable problem in general. That's why the Storm Improvers doesn't even implement a heuristic to try to figure this out, because it gets extremely complicated extremely fast. And so shows this bunch of things here, because cannot try to do the heuristics over a measure of termination of things getting small. And there is a whole chapter at the end showing how to fix this. And interesting. There is this, there is a proof that k is okay. Termination by n. Interesting. Okay. Wait. Okay. Okay, if I do not have this, what's gonna happen? Failure to prove termination is have termination by or decreasing by. Oh, it's trying to prove that gets stuck when n is not smaller than k, which can be the case sometimes. Termination by, and why does 1 plus here? Oh. Okay. Interesting. Interesting. Well, I think I'm satisfied with where we got with what we covered today. I think I'm gonna stay here. Feel free, people in the chat, if there is still anyone. I don't know. Oh, there are a couple of people. Hello, people. Feel free to ask something, to ask questions. I usually aim for these sessions to be 2 hour long. So today we are not, we didn't fill the entirety of the 2 hours. But so tomorrow we're gonna have some polymorphism. Not tomorrow. Oh yeah, that's something too. I don't think I am going to stream Thursday. So Lean 3 streams are Tuesday, Thursdays. Thursday is a national holiday, which is the day of the worker, the Labor Day. Yeah, it's International Labor Day, and the way that we celebrate Labor Day is by not laboring. So it's a national holiday. I think I'm gonna take that off and take my mom to the movie, something like that, something nice, and then I will move this stream to Friday, if you guys don't mind. And okay, so polymorphism, we're gonna be talking about a bunch of arguments and then we start talking a little bit about lists. Cool. This is interesting. Again, thinking a little bit again on what David has in mind when he is writing this book, because it initially strikes me as surprising that he will be talking about linked lists, because that's not how we call it in functional programming languages, because they're not like, there's no links here. Like it's not really a link. It's just, building constructors on top of each other. So it's not as in C, where you actually have a physical pointer linking the datas, right? Don't have that. They're all one very big chunk of in the memory, kind of. I don't know how they do that under the hood, because Lean is originally implemented in C#, in C++. So, but I think the main reason is that they're really teaching for people who does not have experience with functional programming languages. So it's explaining, kind of like making links between functional programming languages and imperative languages, OO languages, the more mainstream stuff. And okay, so yeah, this is all stuff for next session, and a little more on the built-in data types. Okay. Some messages. Yeah, a lot of exercises. Zip. Okay, that should be fun. That sounds interesting. Sounds cool. Then after that, conveniences, yeah, implicits, pattern matching stuff, local definitions with let. Oh, this let's defining an actual function. Okay. Okay. Mm-hmm. Mm-hmm. Anyways, they have different colors for the thing. That's really cute. I prefer light. Okay. Step by step. Oh, monads. Cool. IO. How would you like to be addressed? Cool. Wow. Wow. This really takes the language to another place. Cool. And files and all of that. Very cool stuff. Very cool stuff. Okay. So